These next problems will be tailored to continuing to practice the double angle identities. That's their sole purpose, just continuing to practice them. Now, these examples are going to resemble things we did for inverses because we're given what a trig function is equal to. We're not given the radiant, but we're given the terminal point. And that was something similar that what we did with inverses, and that was because of the given information, we can create a right triangle. Because we know sine is equal to opposite of theta over hypotenuse. Now, if you're wondering why did I do this in the second quadrant, well, the given information tells me that I have to be between pi over 2 and pi, which is exactly the second quadrant. And I can find that x coordinate by just using my Pythagorean theorem. Equals 5 squared, which will give us x equals, and then we're going to do the square root property, right? And it's plus or minus every time you do the square root property. Now, because we are in quadrant 2, we know we're going to be working with the negative. So that's going to be 25 minus 9, which is going to give us negative square root of 16, and that's going to give us negative 4 for the x. Right? That's what we can do with this given information. But the goal is to find these values, right? We don't know theta, but we do know the triangle theta creates, and in a particular quadrant. So if I'm trying to find sine 2 theta, well, I know sine 2 theta is my double angle. That's 2 sine theta times cosine theta. And luckily, I know what sine theta is equal to because of the given information. So this is going to be 3 over 5. And I don't know cosine, but with the triangle I created, I know cosine is adjacent over hypotenuse. So it'll be negative 4 over 5. And then if we multiply this out, this is going to give us negative 2 times 3 is 6. 6 times 4, 6, 12, 18, 24. And then we multiply the denominators. 5 times 5 is 25. Then we have to use cosine theta. Now, luckily, there is various options for cosine 2 theta. There's a couple ways to go about this, right? One way, we can completely avoid ever have needed to even make this triangle, because I know cosine 2 theta, one version of cosine 2 theta has sine inside of it. There are the other two versions that have cosine, but I wouldn't need cosine at all if I used 1 minus 2 sine squared theta. And don't forget, I have said before that this 2, even though it does feel like it's part of the function, you can always pull the power out, both of these notations are equivalent to each other, because once I do that, I would have sine theta quantity squared. And once again, we know what theta was, sine theta, from the beginning. So it'll be 3/5. And let's not forget, when you raise a fraction to a power, you can apply that power to both fractions. Leave me a 1 minus 2 times 9/25. And this 2, don't forget, it's like saying 2/1. So that's going to give us 18/25. But to be able to add this with 1, we're going to need 1 to become 25/25, because the goal is getting the denominators to be the same. And now when I subtract, that leaves me with 7/25 as my answer for the double angle. Now all I'm missing is my tangent to theta, which I will let you finish that example. Right here. And we have, what the identity is, and you can apply it here. And for the sake of time, we'll jump to another example. Once again, very similar. We have to find the exact values of these double angle identities given tangent theta is equal to -12/5, but limiting theta to be between 3π/2 and 2π. Meaning this is going to be in quadrant, right? We're talking about quadrant 4. So if I were to draw my triangle, we're talking about triangle in quadrant 4. This is the theta in question. And let's not forget, tangent is equal to opposite over adjacent. Now, the question comes, where does the negative pertain to? Well, in quadrant 4, our x-coordinate is positive, our y-coordinate is negative. So opposite was going to be -12, and adjacent is going to be +5. And, of course, we can use our Pythagorean identity to find our hypotenuse, right? Our hypotenuse is just taking 5 squared plus -12 squared and equaling to the hypotenuse squared, which would give us square root of 169, which would be 13. You can plug that into your calculator. I just don't want to spend too much time doing those calculations. Now to continue. So sine 2 theta. Once again, sine 2 theta is equal to 2 sine theta cosine theta. Now in the previous example, we already had sine theta, so I needed to find that value. I didn't need to, sorry. But here, I need to use this triangle for both sine and cosine. That would give us 2 times sine is opposite over hypotenuse, which is -12/13, And then cosine is adjacent over hypotenuse. And for the sake of time, I'll let you multiply these numbers out to not make a very, very long video. Then we have cosine. So cosine 2 theta is equal to, and once again, you can choose any version of the double angle. Here, there's no version that involves tangent, so either one is perfectly fine. I'd probably stick to just a version that just has one trig function in it. Again, you could do cosine squared minus sine squared, but you'd have to do the work twice for this triangle. But here, all I have to do is 2 times 5 over 13. That's what cosine is. Because I put the square out minus 1. And I'll let y'all finish the work for that problem. And then we have, last but not least, we have tangent 2 theta. Which we know is 2 tangent theta all over 1 minus tangent squared. Now luckily, tangent was given at the beginning, so I didn't need the triangle for tangent. This is just going to be 2 times negative 12 over 5 all over 1 minus negative 12 over 5 squared. And I'll have you practice your algebra to finish, or your arithmetic, simplifying these, right? Getting the numerator to one single fraction, denominator to one single fraction, and then you can multiply by your reciprocal. But again, this example is just tailored to using your double angle identities and finding an exact value by given the parameters that allows us to create a full triangle that, even though we don't know the radian, with this triangle we can still find the terminal points of the given information. So I'm going to stop the video here. And like I said, there's another portion, and that's looking at half angle identities.